We are about to see Ole Barnov Nielsen reminiscent and explain about the SAM project in the University of Aarhus, an interdisciplinary project that started around 1975 and still continues nowadays. Actually, we are in the basement of the physics department of the University of Aarhus, where, as you can see, there is a lot of going on around this project in collaboration with the European Space Agency. One of the goals of this video is to show a successful example of the role of probability and statistics in the physical sciences and the ideas and developments in these disciplines that arose from this SAM project. As president of the Bernoulli Society, I would like to mention in this connection that the roots of the Bernoulli Society go back to 1975, and in particular to the International Association for Statistics in the Physical Sciences that had Kolmogorov, Neyman, and David G. Kendall as some of its presidents. To continue with the goals of this association, in 1975, the Bernoulli Society set up the Committee for Probability and Statistics in the Physical Sciences. It is the intention of the Bernoulli Society to revive this committee with a more general ambit and profile that reflects the enormous impact during the last 2 decades of stochastics in science. It is hoped that this renewed committee will take up the production of more videos similar to the one you are going to see.
In a sense, it all started in the early 1970s when I was approached by the then professor of geology and sedimentology, Jens Thyge Møller. He and some of his colleagues were very interested in studying the physics of blown sands and also sand transport in water. And they were very worried because they thought they had a serious problem with their laboratory equipment or procedures. They were very, very careful in doing their experiments, but consistently they found something which contradicted what was the then general folklore in the area about the particle size of sand grains. So the problem was this: you go into the field on the beach or inland where you have sand dunes, and you pick up a sample of sand, say from the very surface of the dune. You bring it to the laboratory, and then you separate the grains according to size. And the way you do it is by using a stack of sieves with a finer and finer mesh. So you put the sand on top, then you have this stack of sieves, and you have a machine that does a jumping behavior, and in this way the grains are separated. And then you weigh the grains from each sieve, and that essentially gives you the a histogram of the size distribution. And it was obvious that since these weights are positive, you would rather look at the logarithm of the sizes and plot them in a normal probability plot. And the folklore had it that, of course, this had to be a normal distribution. And I think part of it was based on the knowledge of Kolmogorov's result, that if you take a piece of stick and chop it at random repeatedly, then you get, in the end, for the lengths, the log lengths will be normally distributed. But it turns out that this is completely false, an erroneous interpretation. In retrospect, the explanation is, no doubt, that what is behind the distributions you see is the packing of the sand grains. The wind is moving the sand grains along, and they are packing them according to where there is a place. If a large grain can find a place among the smaller ones where it lies shielded, it will stop there. And so I think it's very much a matter of the packing of the sand grains. And in fact, if you go out into the beach, or you will know it also very well from the shore at the bottom of the sea, that the surface will seem very, very firm, but you can just with your hand do like that and spread the grains. So I think the real explanation behind the characteristic shape of the distribution that you see is a packing phenomenon. Anyway, always when they plotted on log probability paper, they didn't get a straight line as it would have been if the distribution was normal, but they would get an S shape. But people didn't like that because it had to be log normal. So they began to speculate whether the lower part had to do with, for the light grains, that these were grains in suspension. That's one of the ways that grains are moving. Then the middle part was from the grains that are in saltation, lifted up and having a trajectory like a cannonball. And the largest grains were moving according to what is called creep, where they more or less just roll along at the surface. Now, to kill that hypothesis, we went out to the west coast and we collected grains by, in a plastic bag and brought it back and analyzed it. And again, you got this S shape. But Jens Thyge Møller came to me with this problem and brought with him a book that he thought might give some clue to what was going on. And this is a wonderful book written by Ralph Elliott Bagnall called The Physics of Blown Sand and Desert Dunes. This is a very, very famous book. Bagnall was an engineer from the British Army, and he had a fantastically interesting life, both as a scientist and as a member of the British Army, that I could talk about for hours. Maybe I can say a bit more about Bagnall later. But in this book, he showed log histograms of samples of sand grains that he had collected himself in the Libyan desert, and some also in a wind tunnel he constructed himself back in his home in England. He got so interested from what he saw in the desert that he took leave of the army, went back home, built a wind tunnel and did experiments. And that resulted in this marvelous book that is really a key collection of information, and he sort of almost founded this field in this way. But he was not primarily a mathematician. And what he said in this book was that the shape of the log histograms looked not like a parabola, as it would if it was a normal distribution, but it looked like a hyperbola. And that's where I took my cue from this, and I wrote up the mathematical equation for a hyperbola and raised it to the exponential power and tried to find the norming constant. And it turned out that this could be expressed in terms of one of the classical Bessel functions, K1. So you have this log histograms where the log of the density is like a hyperbola. And this came then to be known as the hyperbolic distribution, and which went a very long way to fit the data very well. And this was the starting point for a project in the study of granular material, especially sand in wind and water, that has been going on since. In the beginning, it was just a few people from here, Jens Thyge Møller himself, Christian Dalsgaard, and Hans Kuhlmann from Copenhagen. But gradually it grew. More and more young people got interested in it. People like Kjeld Rømer Rasmussen, who is now responsible for the wind tunnel that we built. And maybe we can go and have a look at that later. And it became obvious that there was so much in this area that it would be worthwhile to try and invest a lot of time and effort and try to raise money to study this on a very broad basis. There was, in the early phases, Preben Blæsild, Flemming Abildgaard. And as the project grew, I realized that to get very far with this and into a study of the related problems of turbulence, we would have to get some real knowledge about the theory of turbulence, and none of us had that. But then I suggested to two very talented young students that they might take an interest in this whole field, and I convinced them that it would be worthwhile, and I organized that they spent a year at the Cambridge University at the Applied Mathematics department, And these are Jens Lade Jensen, who is now professor in statistics here, and Michael Sørensen, who is professor in statistics at the University of Copenhagen. And I have since collaborated with them on turbulence problems also, and Michael and Kjeld Rømer Rasmussen are continuing the work about aspects of all this very actively, partly in relation to the wind tunnel that now it is, which is the third or fourth version. We started out constructing a wind tunnel which was very primitive, and we had difficulty in convincing people from the Research Council that this was a worthwhile project. So we had to do with very, very simple means. But in the end, we began to get money for it. But one of the stages to get a good fan engine to drive the wind tunnel. It's a SOC wind tunnel. We needed a strong engine, and we didn't have money for it. But Jens Thyge Møller was a very resourceful person, and he wrote to the Danish Air Force and said, "You must have a lot of old engines from your fighters lying around, and couldn't we have one of those?" And they were delighted to get rid of one of these. This is a Rolls-Royce engine, and that worked very well. But now we have Kjeld Rømer and his collaborators have a very advanced wind tunnel that we can look at a bit later. Well, it started out in the early 70s, and I wrote my first paper on this, on the hyperbolic distribution, and presented it. So this was 72 or so, and I presented it at a workshop in the Mathematical Research Center, Oberwolfach, and David Kendall, Professor David Kendall from Cambridge, was there, and he approached me after my talk and said that he knew about Backnold, and that Backnold in fact had become a member of the Royal Society of London from his private work on windblown sand. The amazing thing is that Backnold was never affiliated with any university. He was an extraordinary person in many ways. So David Kendall said, I suggest that you send this paper to the Royal Society and I will endorse it. And so my first paper appeared there on this subject. And he didn't know whether Backnold was alive or not, but he looked into it and he discovered that he was indeed still alive, about 80 then, and lived somewhere in Kent. And so I sent him a copy of my paper, and I didn't know whether he was mentally retarded or ill or whatever his status was. But within less than a week, I had a long letter back from him saying how delighted he was that someone was finally taking up an idea he had suggested 40 years ago. And that was the beginning of a very close friendship and also collaboration with Backnold. I visited him quite a number of times in his home, his house in Kent. And he was also in Aarhus several times, participating in some of our field work. Gradually, the group here grew and grew and became known as the Sand Gang. And Backnold participated in some of our work, and he was made an honorary doctor at the university here. And on that occasion, with support from the Tuborg Foundation, we made a film that described some of the work going on here, and also some of Backnold's work and life, and that is accessible on the web now. It became clear there was so much in this field that we took the initiative to start or to have a conference, an international congress or conference on Aeolian research. And it turned out that there were small pockets of people elsewhere in the world that was interested also in this kind of thing, and so it was suggested that we organize a second workshop here in this country, and then the Americans took over as well, and there has been a series of conferences on that since then. Then, after about 10 years or so, my interest shifted somewhat towards very theoretical work, especially in likelihood inference. So from the mid-80s or so, I gradually got less and less involved with the project as such. But as we can hear about at the wind tunnel, it has continued in a very active way since then. But I would like to mention here that as a byproduct of the construction, as it were, of the hyperbolic distribution, I introduced what is now known as the generalized hyperbolic. And one of these is the normal inverse Gaussian distribution that just fell out of the mathematics, as it were. And years later, it was realized that in fact, that is very well suited for studying financial data, time series in finance, and especially so in the completely different field of turbulence. And finance and turbulence are among my real main interests nowadays, in collaboration in the finance context, primarily with Professor Neil Shepard from Oxford, and in the turbulence context with Jürgen Schmiegel, with whom I have now had a very productive collaboration for 5, 6, 7 years. Maybe I could mention a little story in that connection. So some 10 years ago, I was given the Humboldt Award from the Humboldt Foundation in Germany. And one of the nice things about this is that it gives you possibilities to have easy access to have young people come to your country. And I had luckily met Jürgen Schmiegel at the Max Planck Institute for Complex Physical Systems in Dresden a bit earlier, and we found that we had very similar ideas, but from a very different perspective. So Jürgen is primarily a mathematical physicist specializing in turbulence. And so we managed to have him come here under a so-called Fyodor Lynen stipend that is part of the what the Humboldt Foundation does. And I'm very, very pleased to say that we have been able to persuade him and his Lebensmensch, Daniela Meyer, to stay on here for a period with money from the Carlsberg Foundation and now from other external means. But I could just mention one thing that I think is, at least as an anecdote, is interesting, that the then Bundespräsident of Germany, of the Federal Republic of Germany, came to Denmark to meet the Queen, and he was asked to have a meeting with journalists. But he said, no, I don't want to talk to journalists. I want to talk to Humboldt stipends and Humboldt fellows. And this was then set up at Louisiana, the famous Museum for Modern Art in the northern part of Zealand. And we met up there, about 10 people or so, and waited in the cafeteria. It was an ordinary day, so the museum was open, people were sitting there, but a little part of the cafeteria was set up for us to have a cup of coffee. And I was amazed to see that Johannes Rau came with his wife and an entourage of people, someone from the military, a lot of military, but there were not the police around. It was all very relaxed and so on. And I had been asked to say something about Denmark and Germany, and I did so. And I took the occasion to mention Oberwolfach, that I knew that they were in very strong, very difficult financially. The buildings were deteriorating. They didn't have enough money for the library and so on. And I said, you have in Germany a real jewel there that mathematicians all over the world look at with great admiration and fondness. And I noted that Rao get assigned to someone, and so at the end of the meeting he said he had taken note of this, and he would contact the Minister of Science and the Minister of Baden-Württemberg, where Oberwolfach is, and see to it that some support were given. And in the end, that turned out to be the case. So we're standing here with Kjeld Rømer Rasmussen that I referred to earlier, and who is a staff member at the Earth Sciences department here, and who has been very active on the whole project since around the 1980 or so, and is the main person carrying on the research here. And we are standing at the basement of the Physics Institute. Where we are was originally the parking area, but it has now been taken over, in fact, completely by this project. The wind tunnel is where it was originally, but of course nowadays much more advanced. And I would like to ask you to tell us something about your reminiscences of the project and about what kind of work is going on right now.
Yeah. At the stage where I entered the project, there had already started coming visitors from abroad. You have always been good to organize international contacts. So we got affiliated with the department at the engineering department at the University of Aberdeen, and that got a lot of lot of valuable information for us, because at that time we had a lot of basic knowledge about science aspect, but none of us were engineers. So it was important to have also practical information when you build a facility like this. So Brian Willits, Professor Willits at the engineering department, was the first that started us improve our facility. So the wind tunnel you see here is actually the third generation of wind tunnel. And the wind tunnel that you mentioned before, where a lot of our basic research was done, and which had a jet engine, was very heavy to work with. It had a very large power consumption. We could almost use up power for the entire building when we ran an experiment. So the wind tunnel you see here is now larger. It has a larger cross section, and it's also much less. The power requirements are much smaller than for the original wind tunnel.
Can you describe this?
As I mentioned, Brian Willits in Aberdeen was one important contact. Another very important contact was made to the United States, to Professor Greeley at the at Arizona State University, and his collaborator. Ronald Greeley has for many years worked with Aeolian matters, not only on Earth but also on Venus and Mars, as you mentioned. And during such very extraordinary conditions, it's important to have a very strong background in engineering. And one of his group was Jim Iverson at Iowa State University, and he came over as visiting professor in 91 and 92, and that's really where I got very much, that's where I started to work at least 50% of my time in this project. So we started to do research on mass transport, which could easily be done in the old wind tunnel. But it was also clear that there were important aspects that we were not able to study. From an engineering point of view, it's important that you control the various forces that are involved in your system. And one of the important forces is gravity. And gravity you can't change and the influence from gravity you can't change in a horizontal wind tunnel like this. So, so we decided to build a wind tunnel where you could vary the slope, the bed slope of the tunnel. And later on we'll go and look at that wind tunnel.
Is this your own design?
That is, yeah, the sand we have here is a natural sand, but it's been processed in a sieving facility, an industrial facility, where they started out by taking 20 metric tons of sand, and we ended up with 1,500 kilos. They did a marvelous job, and they also told us that they had spent quite a lot more time on this project, so they think they gave a major contribution to science in Denmark.
Yeah. Of course, nowadays the means for measuring particle sizes is much more advanced than in the early days.
Oh, sure, yeah. When we started this, we used all, of course, our basic instruments have been improved. We started out with pitot tubes and we started out with sieves. Today we use laser diffractometry when we study grain size, and also the wind measuring devices that we use is hot wire anemometers, and we use laser Doppler anemometers as well. So that has gradually been introduced as we also shifted our main interest. Where mass transport, which is basically the relationship between the amount of sand, the amount of material that the wind can move under different conditions, that has changed now into a more systematic study of how grains behave when they're in a wind flow. So we study ballistic behavior of the sand grains, and we are involved also, or gradually evolving. That part has gradually evolved into studies where we also interested in the finer particles. Dust moves under the influence of turbulence, and the grain sizes in between dust and sand move partly under the influence of gravity and partly by the influence of turbulence. So that really requires an upgrade of instruments, but again, this allows us to go much deeper into the processes, the basic physical processes that governs sediment transport by wind.
It's a bit mundane thing, but very crucial, isn't it, that we were so close together here, that we could go to a few hundred meters indoors even, and discuss ideas all the time. And this field really requires input from a variety of fields.
Yeah, I think that has been one of the important things that for the success of this group, that you've had not only mathematics and geology, but we also had a close collaboration with physics and even with chemistry, and that has also inspired some of our colleagues to find new areas, new fields of interest. One of my because one of my colleagues, who is really a soil scientist, has been following this, and he gradually got interested in the processes that go on Mars. From his field, he knew that they could find soils that looked almost similar to the red Martian dust that people have observed from space during the dust storms on Mars. And and so this has eventually resulted in that a group of scientists between earth science and physics started studying processes that are relevant on the surface of Mars. The advantage, of course, they could build on is our experience with building wind tunnels. Right now, next to us, they're building the third or fourth generation of Martian wind tunnels.
Maybe we should go and just have a look at that.
Yeah.
I'd like to ask, how many PhD students have been involved?
Oh, sorry. Once again,
No, are we on?
Oh yeah, we are still on. Okay.
How many PhD students have been involved in this project? Because it's a very attractive project for everybody, but especially for young people.
Yeah, it's hard to I would say probably 10, maybe more, at least of Danish PhD students. But during the recent years, but also in the past, where we've had visitors coming from abroad, there have been foreign PhD students in doing part of their research here and continuing at their home university. Recently, 2 PhD students from France have completed their study doing part of their research here. So that's of course the beautiful things about international collaboration. You go out and make contacts and do what is relevant and what can be done more efficiently at a foreign university, and go back and continue your work.
It's really a universal project.
Yeah. This is a new facility. The very basic foundation has really been cut through in order to install a new wind tunnel for Mars studies. It will be a very interesting wind tunnel where you can vary atmospheric pressure, temperature, and gas composition, so that you can study material and sensors that are being sent on missions in space before they actually go to this very hostile environment on the surface of Mars. The study or the project here is done with financial support from the European Space Agency, ESA, and from the Willem Kan Rasmussen Foundation, that has given a major funding for building this large new wind tunnel. You can say that this is the final end of the parking facility at this department, because after this has been built, there will be no more room for parking cars here. But it's a very heavy wind tunnel in order that it can stand at very low pressure. So that's why you need a very, very steady support for it, a very solid support. Also, so they are making the support for railway tracks. So the new wind tunnel is put on railway tracks so that it can be moved apart. It'll be very heavy, and you will also need to be able to get through with instruments and stuff for the rest of the basement. That's a part of the physics department down there. So that's why this somewhat odd-looking hole has been made in the tunnel. The wings there will allow the wind tunnel, which is built in section, to be parked away when they need to get through with new equipment for this one. Because funding, of course, has always been a problem, the sloping wind tunnel was built so that it can use the same engine and the same run on the same fan that is applied for the long horizontal wind tunnel. And then right now you see at a position where it's sloping 20 degrees downwind. So wind is entering in the top section, and then it's flowing parallel to the surface to the bottom of the fan. But it can also, so that's illustrating processes that are going on a downslope surface, for instance, in a desert. Whereas if you tilt it the other way around, you can illustrate processes, you can measure on processes that are going on an upslope surface. It's, as far as we know, it's the only facility in the world that has this capability of varying the bed slope